Good morning, everyone. Today we are going to discuss domain theory of ferromagnetism. The ferromagnetism, we know that ferromagnetism is one of the strong magnetic material. Within the ferromagnetic materials, there is atom will be there. Within the atom, there is so many unpaired electron will be there. So it's have a more number of unpaired electron, and then after, due to this unpaired electron, each and every atom or molecule present in ferromagnetic material, it's have a permanent magnetic moment. At least they have a minimum magnetic moment. Due to that, even that material have a spontaneous magnetization. Spontaneous magnetization means we no need to give any external force to convert it to magnetic material. It's already magnet, so that's why it's called as a spontaneous magnetization. Uh, Due to this magnetic property, this ferromagnetic material, it will allow all the magnetic field pass through in a ferromagnetic material. That's why the susceptibility considered as a positive as well as large. It mainly depends on temperature. In low temperature, those material exhibit ferromagnetic nature. That means very strong magnet. Suppose if we increase the temperature beyond certain point, it's maybe convert into weak magnetic material like a paramagnetic material. The point considered as a Curie point. The Curie point means in which temperature the material converted to ferromagnet to paramagnetic state. The point called as a Curie point. In that point, the atomic magnetic moment will be disturbed by thermal energy. That's why it's converted into strong to weak magnetic material. So these are some of the material. It have a ferromagnetic nature like iron, nickel, cobalt, and gadolinium. To explain this ferromagnetic material, we proposed domain theory. That means ferromagnetic material have a domain, magnetic domain. That means it's a small area. Within the area, all the atomic magnetic moment will be aligned in a particular directions. So each domain act as a magnet, individual magnet, or it separately it have a north and south pole. So you just see the diagram which is given below. There I just mentioned by a arrow mark in a red color, like red color. So it's exhibit a magnetic property of each domain. So each individual domains may be separated by a domain wall. It's also called as a Bloch wall. These are the energy responsible for formation of magnetic domain in a ferromagnetic material, like exchange energy. That means the interaction of magnetic force between one domain to another domain, or one magnetic material to another magnetic material. And potential energy, that's inbuilt energy of materials. Anisotropic means it's a direction dependent property. The response of magnetic field in ferromagnetic material will be different with the directions. That's property called as anisotropic. This behavior will vary one domain to another domain because every domain will align in a particular directions. So the direction dependent property is called as anisotropic. And then after magnetostrictive. So magnetostrictive means it's nothing. If we apply magnetic field in a particular direction in magnetic material, their volume will be changed. Whether it will increase or decrease depend upon the direction. So that's why it's called as a magnetostrictive energy. These four type of energy is responsible for formation of domain. The process of domain magnetization. So how we can magnetize by applying external magnetic field. So these things we can categorize into two types. Suppose in low external field, at low magnetic field, the domains which is aligned in same direction to applied external field, it will start to grow. If suppose if a domain aligned in opposite direction, it start to shrink. So this will kind of behavior will happen in low magnetic field. Suppose if we applied high amount of magnetic field in a magnetic material, so all the domain present in magnetic material it will align in the field of applied in the direction of applied field. That's called a rotation, domain rotation. So by applying external magnetic field, we can convert all the domain in same direction. Without any field, the domain will be aligned in random directions. Due to the random orientation, we cannot able to observe net magnetic field or net magnetic property. By applying some amount of external field in that magnetic field, we can able to rotate all the domain in particular direction, and then we can make it as a strong magnet. Okay, initially in a ferromagnetic material, we are going to increase small amount of external magnetic field in a particular direction. So that particular direction I consider as it is represented in a positive x-axis. If I increase external magnetic field, the magnetization of magnetic material also it will linearly increase up to a certain point. At particular magnetic field, it will reach a maximum value. Then after we cannot able to magnetize any domains or any atomic magnetic moment in that material. So that point called as a saturation point. Then after, if I reduce strength of applied magnetic field in the directions, the magnetization also it start to reduce, but it not follow the same path as it previously created. So here, as we previously discussed, the 4 type of energies involved, because there is anisotropic, that's direction dependent property. If we change the direction of external magnetic field, the response of magnetic material also will be changed. So that's why there is a small lagging in the graph. Suppose then after I'm going to reduce the applied magnetic field direction, the magnetization also start to decrease. If I remove all the field in the material, that means zero magnetic field, still that material have a small amount of magnetization. This is responsible for spontaneous magnetization of material. Even in the absence of magnetic field, it will have a small quantity of magnetization. That's parameter called as a retentivity. Again, what I'm going to do now, I'm going to apply magnetic field in opposite direction, in negative x-axis. If I increase applied magnetic field strength in negative x-axis, the spontaneous magnetization also start to fall. In certain magnetic field, it's become a zero. So here the graph gives idea about how much a field required to demagnetize material in opposite direction, to convert spontaneous magnetic material into non-magnetic, zero magnetic material. That field called as a corrosivity or corrosive field. That field should be applied in negative direction. Again, I'm going to increase magnetic field strength in negative x-axis direction. So then after, the magnetization is induced in that material, and it will start to align in opposite direction as we applied in the same direction to external magnetic field. So that's also increased. Again, the same as we discussed in positive side, here also we will get same saturation, but it is in opposite direction. So remaining things are same. Whether we increase the field in a particular direction, the magnetization will achieve maximum value, that's called a saturation. Then after, if I remove all the field, if we remove all the field, it will have a spontaneous magnetization. To reduce the spontaneous magnetization, we need to apply magnetic field in opposite direction. That's called a corrosive field. So these 3 things are important: saturation point, retentivity, and corrosivity. These 3 things are important. By using these 3, we will get all the information. In case of data storage purpose, it should be in a rewritable. It should be in a rewritable. In this case, if it is a magnetic storage device, by applying magnetic field from this point to this point, we can able to change the binary digit 0 to 1 by changing the direction of domains. So this is a field required to change the orientation of domain. So those things I just explained in the second graph with the domain. From this hysteresis loop, we can categorize magnetic material into two categories, like a hard magnetic material and soft magnetic material. In hard magnetic material, the hysteresis loop area will be very large. So that means it's required large amount of magnetic field to attain saturation in a particular direction. In same way, it's also required huge amount of magnetic field in opposite direction to convert into non-magnetic material. So this is a case in hard magnetic material. On other hand, soft magnetic material, it will have a very small loop area. Just small field is enough to get a saturation magnetization or convert magnetic material into non-magnetic material. And then the loss associated with the magnetic material also, it's directly proportional to loop area. If a material have a high hysteresis loop, it have a more magnetic losses will be there. So these are some of the material. It will exhibit magnetic nature, like a hard magnetic nature, alloy of aluminum, nickel, and cobalt, chromium steel, tungsten steel, carbon steels. So this kind of material exhibit hard magnetic material. And likewise, the alloy of iron and silicon, ferrous, nickel, ferrites, garnets, these have exhibit a soft magnetic nature. Okay, so this is a short overview about ferromagnetic material. The remaining things will next in our next session. Thank you all.